Hi, my name is Andrew McLaren, and I'm here to help you with the classic problem where you've got one object that is moving at a constant speed, another one that starts still, speeds up, and then eventually catches up. We're going to be using what I call the triangle method, um, which is essentially using these velocity time graphs to see an interesting fact that just makes these problems very, very easy. So if we're looking at these two objects, they are moving at different speeds throughout their motion, but they have the same average speed. So if we want to think about our truck, it's going at some constant velocity for some given amount of time, and you can think of this as its change in x. That area is its change in x. Also, you're going to have something that's speeding up, and eventually, with given enough time, its change in x is going to be equal. Like those two areas are equal of that rectangle and of that triangle. And that's when enough time has been gone where they have the same V average. So we can say that this number right here is the V average for both the red object, what we are saying is the truck, and the blue object at a certain amount of time. And when they get that, that happens to be when they have the same amount of area that they've traveled as well. You can kind of see it visually in here. And if you think about the V average formula, what happens is the initial velocity right here for the blue object, that's going to be 0. And then the V final and the V initial, these are both the V average for the thing that just has the same speed throughout its whole motion. So whatever that number is the V average number. You're adding up two of them and then dividing by 2, so it just is the V average number throughout its whole motion. You might notice that the maximum speed at the end for the object that we've got marked in blue is actually twice as high as the V final of the truck. So it's literally just going twice as fast at the very end if it was started at being still at the beginning. So these types of problems, you're basically saying, when will I get going twice as fast as my average speed? So we know that our average speed for this problem is going to be 20.54 for both of our objects moving. And that means we just need to figure out at what time we get going twice as fast. So in other words, we've got this VC final divided by 2, because that plus 0 divided by 2 would give us this number. So the VC final in this problem is just twice the average. So it's fairly straightforward to calculate that number. These objects will have caught up to each other, in other words, when this thing's going twice as fast as the other one. So we've got that 20.54, just times that by 2, and we get 41.08 meters per second. And that is going to be useful because we can figure out how long it takes for that to speed up. So for this object, it's got some sort of acceleration, which is equal to its change in velocity over change in time. This object was starting with a V initial of 0, and it got up to a V final of 41.08 meters per second. And it does that in a given amount of time. So we're just going to call that t. We do actually have acceleration right here, and this is something that's pretty easy for us to get from our earlier calculation. So the acceleration value that we had was a positive 6.31 meters per second. We just need to figure out how much time we need to pass at that rate of acceleration to get up to 41.08. So we take 41.08, you can see that we've just got to rearrange and get that down here and the time up there. So we just divide that by 6.31 meters per second squared. and we get this is going to take 6.5103 seconds, and we're gonna have to round it to our sig figs, but that's how much time it takes for this thing to get going up to that speed. In other words, if we want to plug it back into here, you would get 6.31 meters per second squared if you had this change in speed of a positive 40.08 meters per second in 6.5103 seconds. And we can double check that pretty easily. Just do their 41.08 divided by 6.5103. Yeah, it looks like we're getting that correct amount of time. So this is the amount of time it takes for us to get sped up. And then if we want to figure out how far this has traveled, you could do the blue graph and work with its initial velocity and its rate of acceleration. That would be totally fine. But the easier calculation is going to be working with the one going at the constant velocity, because the change in x is just going to be its velocity, which is just an average or like constant, times the time. Now you could consider the at squared over 2, but this value was 0, so this whole thing we can just ignore. Because the v initial is the v average. We're just gonna work with that number times the time. So it was this happened in this amount of time right here. I am going to use the unrounded number for this next calculation, though we should limit this to sig figs. We had, what was it, 4 sig figs divided by something with 3, so we should have 6.51 seconds really for our final answer. So actually I'll go ahead and box the number when it's been rounded. I'm going to use the unrounded number though, because I'm kind of reporting both of these out at the same time. That's just how much time it takes for us to get to this point right here when they've gone the same distance, and we can see that visually. So we've got our speed, our v average of 20.54 meters per second, which is just that constant. We just times it by the time. 20.54 times 6.5103. Oh, hold on. We missed the decimal point. Okay. We're getting a distance of 133.72 meters, and we're going to limit that down to, because we originally had 4 sig figs and 3 sig figs, we got to limit this down to 3. So it's 134 meters roughly that this has traveled. And we could confirm it if we wanted to using the change in x formula here with that v naught t plus at squared all over 2. I'm going to leave that as a challenge for you in this video. This had an initial velocity of 0, so just ignore that, and you should be able to plug in your acceleration, your time value, and confirm that it's gone 134 meters, like what we saw in this visual proof. Yeah. Thank you for joining me. Let me know if you've got any other questions. I've got other videos like this one where I do a method that is a bit more math heavy and not so much the visual, but it's the same sort of relationship that we're showing here, just looking at it from a different perspective. And I'll have a challenge problem where they don't both start as stopped as well as another video if you'd like to check that out. That should be linked in a little playlist here in the video's description.